All right, so on to question 2. Again, this time what I really want to do is we've done a lot of the heavy lifting here. So again, I'm trying to do the questions in 15 minutes. I have not looked at the scoring guideline, trust me. I want to review myself just as much as you. Again, I might at times flip to the answers to make sure I don't go down a wrong rabbit hole too long, but here we go. Right off the bat, we have a very unique question right here. We need to solve for the sample size that was used. Okay, here's how we can do that. If we're doing a 95% confidence interval for proportion, then we are using a z-table, or a z-value. So I'm going to scroll to actually my t-table. Remember, at the bottom of the t-table, you can see your confidence interval z-values. These bottom ones right here are z-values. So for 95% confidence, our z-value was 1.96. All right, awesome. You know that now. Now from there, the other thing I know is I can actually calculate what the middle value was. So remember that a confidence interval looks like this: point estimate plus or minus z times square root, now it could be z or t, of square root of p hat times 1 minus p hat divided by n. We're trying to solve for n. Now the other idea there is, remember that this right here is an interval. It's saying whatever this value was minus something is this value right here. And then whatever that value is plus something, well, that's right here. And if we want to find out exactly what's in the middle before we add or subtract any value, well, then we simply need to find the average of those two. You get away pre-cal. So if I have 0.584 plus 0.816 and I average those out, turns out our point estimate, or our estimated, or our sample proportion that we got must have been 0.7. So evidently, 70% of his students answered yes, they recycle. The question is, what is n here? Now, the idea is we now know what the middle value was. Let's think about this. The middle value to either this higher number or lower number is found by adding this whole thing. All right, now, in other words, 0.7 plus what gets me to 0.816? Well, we just subtract. So 0.816 minus 0.7 is that far away. So evidently, our z-value times that standard deviation for a proportion is 0.116. That is what we added to 0.7 to get the 8.16. That's what we subtracted from 0.7 to get the 0.584 on the other side. Well, again, we're trying to solve for n. We actually know the z-value is 1.96. We know that that square root is going to have a 0.7 and a 0.3, so 0.7 and 1 minus 0.7, all divided by the root of n, 0.116. And now it's time to do some algebra and solve. If I were going to do algebra, and I'm going to do this a little quickly, I would first divide the 1.96. Now I technically have the square root isolated, so then I would square both sides. And from there, let's see here. I'm going to do some nifty algebra tricks here. What I technically have now is 0.7 times 0.3 over n equals 0.0035. Usually it's good to round to 4 places or more. Actually, for my intermediate work, I usually round to like 6 or 7 just to make sure nothing crazy happens, because some decimals can make a difference. So I'll go to 0.027. The idea is this is 0.7 times 0.3 over n. N is on the bottom. This whole thing is technically over 1. So here's what I can do. I can flip both sides as long as I do that correctly. I have n over the 0.7 times the 0.3 is equal to 1 over the 0.0035027 that I'll round in a minute. Now to get n by itself, I need to multiply by that 0.7 and 0.3. So n is 0.7 times 0.3. When you multiply, it'll go to the numerator over what we had before. Goodness, not going out of this question. However, I'm having to definitely talk through it all, so that's eating up some of my time. 5. Okay, so it turns out we would say that the teacher likely sampled 60 students. Right, so we would say approximately 60 students. All right, given that the method used by the environmental science teacher collects his response, explain how bias might have been introduced and describe how the bias might affect the point estimate. So in other words, there is bias here, and how did that swing the 0.7 that we got? Again, that is the point estimate. That's the one single value that we then can find a range to form an interval in between. Now, I'm going to say this verbally to save some time, since I've been talking through a lot of the math that I was doing in part 1. And the essential idea is, if you're being asked if you recycle by your environmental science teacher, you might be more incentivized to lie and say that you do recycle because you want to be nice or appease your environmental science teacher when you actually don't recycle. Again, you just want to appease them. Now, what is that type of bias called? That is called response bias. That is where answers are influenced. I'm going to say very broadly, you should be more particular, by the environment. Now, what I mean by that mostly is the way the question was asked, possibly. Actually, no, it's called wording bias. So usually what I mean by environment is, are you at, I don't know, an environmental summit? Are you at some field trip with your environmental professor? Are you being asked by your environmental professor? So usually response bias is you're shifting your response based on who asked the question, where you're at, other things of that nature. Okay, so now what that means is, if you would, think about this, if you are being asked by your environmental science teacher, you want to appease him, you probably would answer yes more than no if you're going to lie. So in other words, we would assume that this point estimate is likely higher than the true answer because more people would answer yes to, again, appease their environmental science professor or teacher. Okay, now up next, this is my least favorite part of the question. I might have to go to the scoring guideline and figure out what's going on here. I just remember this, looking at this last year and thinking, what the heck? Okay, anyways. To essentially obtain a less biased estimate, the stat teacher uses an alternate method for collecting responses. A random sample of 300 was selected, and each student was given the following instructions. So first, you flip a coin. If you get heads, you have to say you don't recycle, which is kind of weird. If you get tails, then you truthfully respond yes or no. What is the expected number of students from the sample who would be required to respond no because of the result flipping in heads? That's easy. You would expect 150, since a coin has a, I'm going to write it like this, kind of non-mathy, but a 50-50 chance of heads or tails. Again, I'm just kind of shorthanding here for sake of time, although I'm actually doing pretty good on time, but oh well. Not sure what's going to happen in part 2. So again, you would expect 150. Has 50-50 chance of heads or tails, so expecting half of flips to be heads, 1/2 times 150, or sorry, times 300, the total, gives you the 150. And I'm probably over-explaining this, but I want to finish this and then get to the scoring guideline. Part 2. All right, the results of the sample this time showed that 213 of the selected responded no. Based on the result of the sample, give a point estimate of the proportion of all students who would respond yes to the question. Okay, now this time, this question I'm pretty sure is really, really funky. I'm going to quickly write something down and then go to the scoring guideline. The idea is, based on the results, give a point estimate for the proportion of all students who would respond yes. Now the thing is, it is definitely not just this subtracted from 300, and that is because some of these were forced answers. They were never given a chance to respond. So what that means is, we first have to say, we expected 150 out of 300 150 of 300 were forced to say no. And that means that we can look at the remaining. That means we expect that, well, if 150 were forced, how many were not forced that make up the 213? 63 of the remaining 63. The remaining 150 were able to answer, and 63 out of the remaining 150 would be our point estimate. Now again, hopefully I'm right. Oh gosh. Just remember this question being really, really funky. Honestly, if it were my first time seeing it, I'm not sure I would get that answer. Oh gosh, dang it, I was halfway right. Okay, so let me clean this up real quick. That means we're able to answer, sorry, got this wrong. Hopefully you already looked at the scoring guideline and knew that, but again, I'm trying to be true to taking this exam. So again, 63 of the remaining were able to answer and said no. So then that means, well, if 63 to 150 answered no, then that means 150 minus 63, 87. Said yes, and so 87 out of 150 is what you see there. Okay, let's go to reading the responses. So again, that part 2 is super confusing the first time you see it. It's a weird, wacky question. Hopefully the other 2 parts went by pretty quick. Really, it's just part 2 is the most difficult part. Anyways, how do you get your essentially correct in part A? Well, first let's see if I got the right answer. That'd be nice. Sample size was 60. Cool. Okay. You use the standard error, where p hat's between 0 and 1. So in other words, you can see that at least I had this somewhere in the problem. So check. Shows evidence to p hat being 0.7. Now I did this mathematically, but I didn't actually write out the calculation. Oh, show that it was used correctly in the standard error. Okay, awesome. Yeah, I put that in the standard error correctly. Yay. I didn't have to calculate how I got that, just to show that I was using that in my standard error. I have to show evidence that 0.116 was used correctly in the calculation. Again, I think I've done that. Show evidence that 1.96 was used correctly in the calculation. So really, it's just, did I show my work? Is really what this is all saying. Includes a single positive whole number answer, because you definitely can't sample 59 point whatever students, so I technically didn't need to say approximately. If you got 3 or 4 of these, you got a P, and if you didn't get 3 or more, you get an I. Okay. You can see lots of different notes about how your response might be correct or not. Algebraic work between the setup and final answer does not need to be shown. Just have I can put up 5. Yeah, so there's lots of different ways to do that. Now again, essentially what that means is you might have actually wanted to write out how you got the 0.7 and how you found the z-value and how you got that 0.116. I verbally stated that, I didn't write it down. So in other words, long story short, always write down any work you plug into a calculator if you have the time. Okay. Part B, explain why the result might differ from the truth. So it wasn't anonymous and it was asked by an authority figure. Student might say yes, again, because of the fact that it's their teacher. Describe the effective bias by the number of yeses, and then it doesn't contradict the bias described. All right, so again, my explanation did that. It suffers, again, from response bias because the environmental science teacher was the one who asked the questions, is what I was saying there. And we explained that it would differ because, again, students might lie and say they recycle when they don't. I definitely verbally said that. And then I did say that we assumed that this would mean we would expect a larger proportion of yeses because they want to, appease or have a good response for their environmental science teacher. Okay, last one in part 3. If you get the answer 150 in part 1, and you get the answer of 0.58, which is that rounded in part 2, that's how you get your E. Now you get a P if you gave one of the answers, if you get the first answer and you got 0.42, like I did. So I would have gotten a P my first time without going back and checking my work, which I would have done if I had the time. Or if you don't give the correct answer, but given a correct answer of 0.58. So, in other words, you have to, if you kind of notice this, you have to at least have one of them totally correct. All right, so just kind of be aware of that. That's really what that's saying. You either got one right and one wrong, but if you get both wrong, you're out of the gate. Actually, what this also means to me is this also means you have to get 150, or you either have to get, you have to get 150 and 0.2 or 0.58. If you get 150 in some other answer, I think that would qualify as an I, all right?